right, Trigoners. So these are notes 4.3. Go ahead and pause the video and read our 6 fabulous objectives for this lesson. All right, so there was a famous mathematician, Gauss, and he proved the fundamental theorem of algebra. The fundamental theorem of algebra guarantees that every non-constant polynomial can be factored as a product of linear factors. So every polynomial of degree n greater than 0 with complex coefficients has a complex 0. Every polynomial of degree n greater than 0 with complex coefficients can be factored as a product of n linear factors. So let's do this first example. So again, we know that this particular polynomial has degree 6. So that means that we have 6 complex zeros. The degree is 6, we'll have 6 complex zeros. So let's think about that. That means that the zeros could be real, they could be non-real. We don't know if, there might be zeros with multiplicities. So for example, this one is factored, so you could say that x equals 0 with multiplicity 2. And then we know if 2x minus 1 equals 0, x equals 1/2, and this has multiplicity 3. And then x equals -3 with multiplicity 1. So we know that's 1, 2, that's 6, so 6 complex zeros. So this particular example had all real zeros. So now we're going to try and graph it. So the first thing that you want to do is look at the end behavior. The degree is even. So we know that if it's positive, right? The leading if you multiply this out, which I don't think you want to, but it would be x to the 6th. Notice it would be a positive x to the 6th. So we know that the end behavior as x approaches infinity and as x approaches negative infinity, your f of x or your y value will approach infinity. We know that the only places that you will have your graph touch or cross the x-axis would be at 0, -3, and 1/2. Those are the real zeros. So now we read a function like we read a book from left to right. So when you get up to the -3, notice that it has an odd multiplicity, so it is going to cross the x-axis. You could say pass. Now when we come to the 0, we know it has an even multiplicity. Even multiplicity will bounce, or some people say touch. Now the 1/2, that has an odd multiplicity, so you will pass, or again, some people say cross. Okay, great job. Let's try number 2. So number 2, it says sketch a graph. So we could actually just use transformations. We know that our parent function y equals x squared. Looks something like this. So this would be moved up 9. But let's think about what would happen if we factored this. If we factor over the set of complex numbers, we would have x plus 3i and x minus 3i. So notice the degree is 2, and we have 2 complex zeros. They just happen to be imaginary. So you have 2 complex zeros, and the degree was 2. Notice that theorem 3. If you have real coefficients in your polynomial, which we do, the imaginary zeros will come in conjugate pairs. So notice we had plus 3i and minus 3i. Those were the zeros. All right, let's do another example. This says, given 2i is a 0, actually it's saying is 2i a 0, given f of x equals x cubed minus x squared plus 4x minus 4. Now there are 2 ways you could do it. Here's one way. Do you remember the remainder theorem? If all we want is the remainder, we want to know if the remainder is 0, then x equals 2i is a 0. So you could say f of 2i and substitute 2i everywhere you see an x. Notice I squared is -1, so this would be 8i squared times I. I squared is -1. So notice this would actually be negative 8i plus 4 plus 8i minus 4, so that's 0. So that means, yes, 2i is a 0. Now, another method you could use synthetic division and put 2i on the shelf. Here are your leading coefficients. Bring the 1 down to get started. So these are not like terms. So you have negative 1 plus 2i. So now I take 2i times negative 1, which is minus 2i. 2i times 2i, which is 4i squared. 4i squared is negative 4, so you end up with negative 2i. Negative 2i times positive 2i is negative 4i squared, which is actually plus 4, so that remainder is a 0. Now, we could try something. Notice if I put negative 2i on the shelf, right? Notice that since x2 equals 2i is a 0, we just talked about how its conjugate, complex conjugate, must also be a 0 because we had real coefficients. Let's give it a try. If you do synthetic division again, you say, yes, it was. So x equals 2i, x equals negative 2i, and then we end up with x minus 1. So x equals 1 is my third 0. So there are 3. It's a cubic. We would have 3 zeros, and there they are. Okay, let's go ahead and find all zeros. So notice for this one, go ahead and pause the video and think about a plan. What would you do to try and find all zeros? Okay, so the problem is, if you wanted to try and do synthetic division, the problem is I know the answer. All the zeros for this one are non-real. So you could factor this one. If you let x squared equal a temporarily, you have a squared plus 3a plus 2. So that would be a plus 2 and a plus 1, but then you realize, well, that's really x squared was a. So notice if you factor, now you'd be able to find the zeros. You could say x plus root 2, but you'd need an I. X minus root 2, and you need an I. X plus I and x minus I. So you have a fourth degree, and you have 4 complex zeros. X equals plus or minus I root 2, and x equals plus or minus I. But again, I think that would have been difficult if you weren't able to factor that one. So what we need to do now is we need some more tools in our toolbox here. Notice the rational zero theorem. The rational zero theorem says, for example, let's say that I have f of x equals 3x squared plus 5x minus 2. And if I asked you to factor that, you'd say, sure, I could factor that. But let's think about it. So now we know that the zeros are 1/3 and negative 2. But when you were factoring, like what were you thinking? What types of numbers were you thinking of? So notice, for example, for this one, the possible rational zeros were factors of the last number, plus or minus 1, plus or minus 2, or factors of the last number divided by factors of the first number. So 1/3 or 2/3. So again, plus or minus 1, plus or minus 2, plus or minus 1/3, plus or minus 2/3. And let's think about why. Because when you were factoring, we needed 3x times x to get 3x squared, and we needed a 2 times a negative 1 to get the last number. So notice when I was trying to think about how I would factor that, I certainly wouldn't have put a 2x here and an x here. That would not multiply to give me 3x squared, right? So that's why the possible rational zeros are factors of the last number, if they're in descending order of degree, and factor divided by factors of the first number. Okay. Okay, so let's do an example. So the first thing you might want to do is say, I'd really like to find all the zeros. What are the possible rational zeros? But again, don't forget, you might have non-real zeros, you might have ugly decimals, but if they're rational zeros, they will be factors of the last number divided by factors of the first number, which here is just 1. So I don't have a calculator. So since I don't have a calculator, I just have to start trying things. So I think what I'm going to do is try 1. Maybe it's a 0. Let's see. So I'll put 1 on the shelf. And notice I need 5 zeros total. So I bring the first number down, I multiply and add, multiply and add, multiply and add, multiply and add. Look at that. My remainder 0. Now, I had a 5th degree, So notice this is actually a 4th degree. I'm not going to write this all out, but notice if I did, this is what I would end up with, right? But the whole idea, we want to whittle this down to a quadratic because we're really good at factoring quadratics. So I need to find another 0. I don't know. I'm just trying. Now, how about -1? Maybe. Look at that. It worked again. I have a remainder of 0. So far, 1 is a 0 and -1 is a 0. Let's try, I don't know, let's try 2. Okay, we were having good luck because, take a look at that. The 2 also worked. Okay, so now we could keep just trying things, or you could realize that the last number is the remainder, then the plain old number, and then the x, so sorry, this would be remainder, right? And then the constant, the term with the x, the term with the x squared, and we know that we could factor this because we're really good at factoring quadratics. So now we know that the zeros, notice I had a -2, if x plus 2 equals 0, and 3. So I had 5 zeros, and here they are. So if I said write as a product of linear factors, that means that f of x is x minus 1 times x, quantity x plus 1, multiplied by the quantity x minus 2, the quantity x plus 2, and the quantity x minus 3. So if you multiplied all of this out, you would get this polynomial right here. Okay, let's do another one. First of all, go ahead and pause the video and write the possible zeros, and then go ahead and use synthetic division to try and find all 4 zeros. All right, so we tried 1, and 1 worked. So there we go. I have 3 zeros left. So I don't really know what else to do, so I think I will try 2. So let's see, 2, it does not looking good so far. Nope, 2's not going to work. I'm not going to get a remainder of 0. So, all right, erase that. Let's try something else. So let's see, what about perhaps -1? Let's try that. And again, I don't want to start over because I whittled it down from a 4th degree to a cubic, so I don't want to start over. So let's see, I bring the first number down. Nope, didn't work. Notice that the remainder's not 0, so that didn't work. I don't know, let's try maybe -4. Let's try that. Bring the first number down. That worked. So now notice I have x equals 1, x equals -4, and again, remainder, plain old number, so this is x squared plus 1. So I know how to factor that. That's x plus I and x minus I. So my zeros are plus or minus I. Again, those conjugate complex numbers come in conjugate pairs. And x plus 4 is a factor, and x minus 1 is a factor. So I found all zeros. There are 4 of them. And I was able to write f of x as a product of linear factors. Okay, let's try these next examples. This time I told you 1/2 is a 0. Well, that was nice that we know where to start. So we need to find 2 more. All right, there's something I want to show you, though. If we do synthetic division, okay, that worked. Notice we're left with 4x squared plus 2, but here's what I want you to think about. When you put 1/2 on the shelf, you are really factoring out x minus 1/2. That's why we kind of avoided putting a fraction on the shelf before. So you really have x minus 1/2 times 4x squared plus 2. So that's x minus 1/2. And then you could factor out a 2. Right, over here, and distribute the 2 over here. So that's 2x minus 1 times 2x squared plus 1. So notice if you multiplied this out, you would get my original. So again, that's why a lot of times people use long division when you have a fraction instead of using synthetic division, because you know that this last line is kind of confusing. I remember my teacher told me, "Oh, you divide everything by 2," but I think that was bad advice because I wasn't really sure, you know, why. What are you doing? And this is why you factored out x minus 1/2. Okay, go ahead and try the next problem, number 8. This time they want you to put 4i on the shelf. Go ahead and pause the video and give it a try. Let's review what we learned in Theorem 3. It says imaginary zeros with real coefficients, if they exist, occur in conjugate pairs. Okay, so in other words, if the polynomial has real coefficients, if, for example, 2i is a 0, negative 2i must also be a 0. Otherwise, the coefficients would not be real. So notice for this problem, okay, the coefficients are all real numbers, so they told us 4i is a 0, so I know right away that negative 4i is also a 0, because they have to come in conjugate pairs. We had real coefficients for our polynomial. So first, go ahead and use synthetic division with 4i, which that's not going to be a lot of fun. So we have 8i, and then 4 times 4 is 16, so plus 16i squared. Don't forget, i squared is negative 1, so the 16s cancel out. Then 4 times 8 is 32, and that's I squared. Remember, I squared is equal to negative 1, so this is 0. So now, I know that looks ugly, but now we're going to go ahead and use synthetic division with its conjugate, negative 4i. The second time is like a walk in the park. Notice that's cancels out, so we have x equals 4i, x is equal to negative 4i, and this is x plus 2. So our third 0 is x equals negative 2. So it's cubic. We need 3 zeros. We just found all 3. Okay, so for this one, I said use your calculator. Let's see what happens. Go ahead and pause the video, type this into the calculator, and see if that is helpful. So very interesting. So it's 4th degree, and all of the coefficients are real coefficients. So I know that if we do have imaginary zeros, they come in pairs, if there are any. So again, or non-real zeros, I should say. So notice that I'm expecting 4 complex zeros. I'm looking at my calculator, and I just see it appears that there's a complex zero at 1. So I will go ahead and think about that. If x equals 1 is a 0, x minus 1 is the factor. So let's try 1 on the magic shelf here. There we go. So we've got 1, negative 3, 3, negative 1. Okay, so 1 worked. Now, I don't know what else to do because I didn't see any other real zeros. And again, we have to whittle this down to a quadratic, or we don't know what to do. So why don't just try 1 again? Maybe it has multiplicity too. And it does. Okay, so notice x equals 1. And then x equals 1 again. And now we're left with x squared minus 2x plus 1, which we could factor that. And we realize that this problem actually has the same 0 4 times. So x equals 1 with multiplicity 4. So I'm not sure if the calculator really helped. But when you looked here, you realize since it bounced at 1, that it had to have an even multiplicity. All right, let's try number 10. It says, write a polynomial of degree 4 with the following zeros. So x equals 1 with multiplicity 2. So that would look like this. Okay. X equals 1/2. Okay, so if I multiply by 2 and subtract 1, so that's another factor, 2x minus 1. And then x equals negative 1, so x plus 1. And notice it's degree 4, and that would work because we have 1, 2, 3, 4. Okay, so the next one, though, is a little bit trickier. Notice that I told you there's degree 3, but I only told you 2 zeros. So pause the video and think about what that third 0 must be, because again, third degree, we must have 3 complex zeros. Okay, so did you realize that since it says real coefficients, right, our zeros would have to be plus or minus 3i. Those imaginary zeros must come in pairs. So we have x minus 2, x minus 3i, x plus 3i, but here's what's also different about this one. I told you a specific point. So that means we have some coefficient a here, and we're not sure what that coefficient is. We need to find it. So there's a point at 0, 1. That's a solution of our function. So that means when y is 1, x is 0. So now if we solve for a, you end up with, let's see, negative 2 times negative 9i squared. I squared is negative 1. So we have 1 equals negative 18a. So a is negative 1 over 18. So here is our polynomial. Great job, everybody. All right, we have 2 examples left. So the next example says, find the cube roots of negative 27. So some number cubed equals negative 27. Well, I do know that negative 3 cubed is negative 27. All right, so notice that this is really a polynomial, degree 3, so we need to find 2 more zeros. So x equals negative 3 would be 1 0. So let's go ahead and put negative 3 on the shelf. We need a placeholder for the x squared, a placeholder for the x. Bring the first number down. We're doing synthetic division. Well, we knew it was a 0, so there you go. So we're left with a quadratic, which we are really good at solving quadratic equations. Now this one I'm not able to factor, so you could use the quadratic formula. So we end up with 3 plus or minus the square root of negative 27, all over 2. So 3 plus or minus 27, let's see, that's 9 times 3. So here are our zeros of this equation, which would be the 3 cube roots of negative 27. Again, it's x cubed, so there are 3. Okay, for this next example, and our very last one, we're going to use our calculator. Pause the video and try and see if you can find the zeros by using your calculator. So our graph looks like it passes at negative 2, or crosses the x-axis, also crosses the x-axis at 1. So we know that we have x equals 1 and x equals negative 2. So let's use synthetic division, because we could, like I said, we need to factor out x minus 1 and x plus 2 so that we could end up with a quadratic, so we could use either quadratic formula or factor. So let's start with, we'll put 1 on the shelf, and we'll use synthetic division. All right, and now, again, we don't want to start over, so keep this line, because like I said, we started with a 4th degree, now we have a cubic. Now let's use the negative 2. So we know that we have a quadratic now, and we could factor that. So here's the problem. Now when we looked at our graph, let's go back to the calculator. Yeah, so notice it was confusing to us because it looked something like this, right? So notice that it passed at negative 2 because odd multiplicity, but it passed at 1 because we actually had a multiplicity of 3. If I factor it, it looks like this. So x equal 1 with multiplicity 3 and x equals negative 2 with multiplicity 1. Those were our 4 zeros. Great job, everybody.